Hello, our team is Nety, and our project is learning network science using interactive visualizations. The field of network science contains numerous concepts and subfields along with algorithms, models, and theories. When we were taking the network science course, me and my teammates, often felt that we could learn the concepts faster and easier with a more visual and interactive approach. Therefore, as our course project, we decided to create interactive visualizations and tools to depict various network science concepts. We therefore created a web app. We created our web app using Dash and Plotly for visualization and also the various NetworkX libraries. The app has a sidebar panel layout. The sidebar can be used to select the network science concepts to explore. We have presented concepts regarding network theory, distribution, paths, centralities, scale-free graphs, communities, and spreading. The user can select from various known networks and explore the concepts and their effects on the network selected.
After learning about the networks, we can and selecting a network from the home page, it's time for us to visualize a network by going to the network theory page. The network theory page renders the network in a graphical format where the nodes are sized based on the degree, and when you hover on the nodes, it displays the name of the node. You can select a node which will highlight its neighbors and the edges between the neighbors. There is a table that also displays the cluster coefficient and degree of each node in the network. You can select a different network right from this page, which will change the graph, and you can visualize the newly selected network. In a random network, you can also change the nodes, which will change the graph display, and you can also change the probability. Thanks.
On this page, the user can view the degree distribution of the selected network. The degree distribution is important because it reveals the overall connectedness and structure of the network. The user can also choose to plot a distribution of a random graph with the same number of nodes and about the same number of edges as the selected network. This feature is really useful in understanding the difference between networks with a scale-free distribution and networks with a binomial or Poisson distribution. The user can also view the log-log version of the degree distribution. So as you can see, this is a scale-free network with a heavy tail, while the random graph is short-tailed and immediately decays. This graph also shows you approximately how many outliers are contained within the network. So this is the paths page of our application. The user can find the shortest path between any two nodes simply by clicking on them. And as you can see, the path will be highlighted. So the shortest path is found using Dijkstra's algorithm because of its efficiency and guarantee to always find the shortest path. Right now, all of the weights are assumed to be uniform. However, at some point, I want to allow different sets of network-specific weights to be utilized. This page also contains a tutorial that the user can go through to understand the concept of shortest paths and the small world phenomenon. As you can see, the Les Mis network is a small world. So even though it has 77 nodes, the user will struggle to find a path length greater than 4. Then the user is prompted to create a random graph using about the same number of nodes and the same number of edges. And the user should find that finding a longer path is much easier when the network is random.
The concept of centralities is very important in network science. Centrality is a way of measuring the importance of any given node, and centrality measures play a huge role in understanding the networks. In the centrality module, you can explore and learn about some of the different kinds of centralities that exist. You can use the drop-down menu to explore one of the listed centralities. Once you select a centrality, you are presented with a brief description of it, and the graph below shows how the centrality measure looks for the selected network. You can explore the same centrality over various networks by selecting from one of the listed networks. By hovering your mouse over the nodes, you can show the centrality value for each node. By selecting a second centrality for the graph below, we can compare two different centralities and their impact on the same network. We believe that this will help understand exactly what feature of the network these different centralities highlight. A scale-free network is a network whose degree distribution follows a power law. A common feature of scale-free networks is the presence of hubs, or a few nodes that are highly connected to other nodes in the network. The presence of hubs will give the degree distribution a long tail. In the scale-free module, you can explore the formation of a scale-free network and compare its properties with a random graph. Notice that we first start with 10 nodes. As we increase the number of nodes, we can observe that there are certain nodes whose degree increases more. These nodes are the hubs. Majority of the other nodes have very small degrees. Corresponding random graph, we can see the nodes follow a more uniform degree distribution. And there is a lack of hubs. In the adjoining graph, you can see the difference in between the degree distributions for the scale-free graph and a random graph. Let's increase the number to 100 to make this more prominent. You can clearly see that the degree distribution for the scale-free graph follows a power law, and the degree distribution for a random graph does not.
Communities are a widely studied field in network science. Communities are subgraphs that have dense connection between nodes, contain a path between each node within the community, and loosely connected to nodes from other communities. Communities are widely studied field, and there is a lot to explore. Over the time, a lot of algorithms have been devised to detect communities. We have implemented two such algorithms, one being Leuven algorithm, which is a two-phase process to detect communities. The other one we implemented was Kirwan-Newman divisive algorithm, which moves the links with highest betweenness centrality. And you can see, the way we implemented is to show it live. Spreading phenomena provides statistical study on how diseases or information spread in a network. With coronavirus pandemic, we have seen the infection spreading in multiple waves. Many models are developed to study the spreads, which then allows officials to devise steps to slow the spread. In the SIS model, the infection spreads at a beta rate and infected people recover at a rate of mu. Visual of this model show how nodes get infected by changing from black to red and then go back to susceptible stage, changing from red to gray. In the SI model, there is no recovery rate. So the infection keeps spreading until everybody is infected.
To conclude, the construction of this app came with many challenges, such as having to familiarize ourselves with front-end technology like Plotly, Dash, and HTML. Moreover, visualizing networks can be costly, and to render visualizations in a reasonable amount of time took much effort. And even still, there is much left to be done to allow the app to run at maximum efficiency. For example, performing big computations with NumPy would have likely increased the speed of many of our operations. Moreover, we could have used a database querying language like Neo4j to save various versions of graphs, then upload them into our application instead of performing computations in real time. Nonetheless, we expect that the tool we created will help those who are curious about network science learn something about some of the various concepts. Coming into this course with little understanding of what exactly network science encompasses, we believe that a tool like this would have been of great use to us and would have provided us with enough information to be confident entering the course. However, there are many concepts within network science that are not contained within the application. The goal is to keep adding to the application as time goes on to create a complete and comprehensive learning tool that could benefit both people new to the field as well as those who are experienced in the field of network science. We also intend to make the GitHub public so that anyone who wants to contribute will be able to.